Vernam cipher, also referred to as the one-time pad, is a type of encryption which is incredibly secure if the principles of the encryption are actually followed each time. So the way this one works is that you have your plain text and you want to encrypt it. In this case, we can see we have the word hello. We have a key, which is the one-time pad part of this, which is a uniquely generated set of letters equal to the length of the plain text phrase. And it has to be random, so using a computer wouldn't generate a random value. It has to be properly random. You then perform an exclusive OR on the actual on the combination of the plain text and the key, and it's that exclusive OR binary value which is then sent to the particular to the recipient of the encryption method. So, in essence, what does that actually mean? Let's try and understand it a little bit more. Let's say we want to send the message hello, and we've been given a completely uniquely generated random key of SKSDI. So it's totally unique, totally random. It has to be totally unique, totally random. So what we would do is we would then take the letter H and the letter S, and we would refer to what they are in their ASCII code table. So we would write out the letter H in ASCII form first of all, which is 104, I believe, and therefore written out in binary, looks like as you can see on the screen, and then the letter S is the conversely what that looks like. We then perform an exclusive OR, and an exclusive OR is something that you should look up if you're not sure on what it means in relation to logic gates. But essentially, if we consider it as a truth table for a moment, an exclusive OR dictates that if we have a 1 and a 0, then we have an OR. If we have a 0 and a 1, we have an OR. If we have a 1 and a 1, that's not an OR because that becomes essentially an and if we have a 0 and a 0, that becomes an X. So these become 1, they become 0, and so on. So let's see how that transfers across. So when we actually perform our exclusive OR on these values, we can see that the 0 and the 1 becomes a 1, 0 and 1 becomes 1, 0 and 0 to 0, and so on. You can see ourselves working our way along. So we prepare the final output statement that's going to then be sent to the recipient of this message, and it's the exclusive OR output is that what we actually are sent, and we calculate it. Now, in this particular example, we could convert it back to an ASCII value and then send that over, but the ASCII value for 1, 2, 4, 8, 16, 24, 28, 29, if I refer to this website, is group separated. It wouldn't really mean anything to us in this case, so we're not going to send that over. What we're just going to do is we're going to send the binary value over instead. Now, when that's been received, the receiver needs to have the ciphertext to hand, but then also the key in which to decrypt it. So for this one-time pad to be as secure as it possibly can be, the actual ciphertext is sent separately to the one-time pad itself, and they will both be received then at the opposite end by the person that's going to decrypt the message. So we write our ciphertext out, which was what we converted using the exclusive OR. We then have our letter S in ASCII, which is our one-time pad letter, and then we perform an exclusive OR, which gives us our value of 104, which is the letter H, or lowercase h, in the ASCII value. That then ensures that we have a totally unique encryption method for every single time that we want to send a value from point A to point B. It has to be a uniquely generated one-time pad, otherwise it's totally useless. But if that's done, and also it is sent separately to the ciphertext, it will work. It will work perfectly and will be unsolvable to anyone that looks at it.